Hi everyone, welcome to lecture 10. This is a short week because of the holiday this week, and so you will just have one blog, one lecture, and then you have your quiz. So make sure you watch this full lecture before you do your quiz. We are now starting off with chapter 4, and this lecture is going to be relatively short. I'm only going to go 4.1 to 4.3. And then we'll develop more of the concepts in the next lecture next week. Okay, so this chapter is looking at reactions in aqueous solutions. And so when I say that, I'm looking at chemistry that's taking place basically in some sort of liquid. Okay, to really understand that, we're going to put some vocabulary words behind that you kind of need to know. So the first one is that anytime we're dealing with a liquid and mixing chemicals, we have three main vocabulary words. I'll pop them all up. The first one is what we call a solution, which is a homogeneous mixture. Homo, when you see that word, get my mouse working. See if I can get my tool working. I can't turn on. Okay, I don't know where it's at. So when you see the term homo, you should think same. And so in this one, a solution is a same throughout mixture of two or more substances. The other terms that we will use are what we put together to get a solution. So the first one is what we call a solute, and that is the substance that's normally present in a smaller amount, and it's normally the powder form or the iron or whatever we're putting into the solution. The solvent then is what's doing the dissolving, and so the solvent is going to be like your H2O or your soda or whatever would be doing the dissolving, whatever the liquid is. And we can use those terms with liquids like I did. So if we're looking at a solution of a soft drink, which would be all these chemicals combined with water. So the soft drink would be the solution or the homogeneous mixture. The solvent would be the substance that's doing the dissolving, which is water. And then your solute would be the sugar and the CO2. But this is also something that we can do with air. So air is a mixture we breathe, but we don't pick out each little oxygen or nitrogen molecule when we breathe. We breathe it all. And so air would be considered a solution. Solvent would be our nitrogen, because that is the main component of air. And then our solute would be oxygen, argon, and methane. Some other things that might be also considered solution solvents and solutes. So these key terms are probably really good to know, especially for your quiz this week. Another term that I want you to become familiar with is what we call an electrolyte. And so normally when we think electrolytes, we think of substances that can conduct some sort of electricity. And it's because generally there's some sort of salt or some sort of positive and negative charges that can connect the conductivity portions of the light bulb or whatever we're using to light these up. So then when we talk about a non-electrolyte, obviously this is a substance that doesn't conduct any electricity. So in this first one, here we probably have a non-electrolyte of maybe water. And we know water on its own doesn't normally conduct a current. A weak electrolyte would be something that would power a light bulb, but only minorly. And then we have a strong electrolyte, which obviously is conducting a really good current here and fully lighting that bulb. And again, this is the presence of positive and negative ions within that solution. So if we have a lot of positive and negative ions, or cations and anions, then normally what we see is a very strong electrolyte. And so what we would normally find is that if we had a compound like sodium chloride, we would know that it would dissociate. And if it dissociates or breaks apart 100%, then we have that strong current conducting power or electrolyte. So this is an example. Here we have NaCl, which is just table salt, but we know we have both the positive and the negative ion. And because when this goes into water, it separates. It gives us that nice charge or way to conduct electricity. Weak electrolytes would be things like this. And this you'll learn throughout the semester as well, so I don't expect you to look at it and know that it won't dissociate completely. But if we look at this compound right here, you'll see that obviously when the reaction happens, it can take place in both directions, but all it's losing is a single hydrogen. And so because it did not dissociate completely, this would give us a weak electrolyte. We still have charges, but it's not a complete dissociation like this one up here. Okay, so some things that you're probably picking up in this reaction that you haven't seen in the last reaction, and that is this double arrow. And so we have been using a single arrow to show that the reaction is going in the direction or proceeding in the direction that the arrow is pointing. But now we're going to start getting into reactions that can not only go this direction and happen, but then they can come back together and go that direction. And so we have a reversible reaction, or a reaction that can occur in two directions. And most of these that have reversible reactions are going to be considered a weak electrolyte because they're not dissociating completely. It's a lot easier to put them back together. And so, for example, like this one, the acetic acid, we know that it is a weak electrolyte because of that reverse reaction. So something else that you kind of need to put into perspective when we're looking at solutions or things that are dissolving other things is the term hydration. Okay, hydration normally means to be full of water, and it kind of holds true for chemistry as well. Hydration is the process in which an ion is surrounded by water molecules. Okay, so here we have a positive ion, maybe sodium, and here would be our negative ion, which would be chloride. And you can see that the water molecules around it are arranged kind of in a specific pattern. And you see that over here as well. We have the whites facing towards this negative charge, and over here we have the reds facing towards it. Now, how do we get that? Let's talk a little bit about this. Again, I gotta see if I can get my mouse to work. Some days it likes to work and some days it doesn't, that's for sure. I don't know why it's not working. Let me see if I can't get it to work on my computer here quick. Okay, so if we look at the water molecule, which is down here, and hopefully this works now. This water molecule. You can see we have an oxygen here, and a hydrogen here. So 8, oops, I was totally wrong on that. Okay, we have 2 hydrogens, man, must be Monday. And 2 hydrogens and 1 oxygen. Now, if we look at how many electrons each one of these atoms have, we notice that hydrogen has 2 electrons. Okay, and then we notice that oxygen has 6 electrons. And so if we look at this model of the atom or of this compound, we can tell that one side is more positive because there's less electrons around it, and one side is more negative. And so looking at it, we know oxygen is more negative because oxygen has 6 electrons around it, and the hydrogens only have 2 electrons. So this side would be more positive, this side would be more negative. And this is the symbology that we use just to denote one side's more positive and one side's more negative. Okay, so in this, what you'll see is that the negative, or the red side, is attracted to the positive, and the positive is attracted to the negative. Okay, so hydration again is dissociating these ions, and then not only dissociating them, but surrounding them completely by a water molecule in this specific arrangement, where positive is attracted to negative and negative is attracted to positive. So when we look at the conductivity, or the way to move a current across these, we're always looking for those positive and negatives. But if there are absolutely no positives or negatives associated with the breakdown of this compound, say for instance sugar, so here's sugar, right? And when sugar is introduced to water, it doesn't break down, it stays sugar. We taste sugar water. And so in that case, these are non-electrolytes. Now this chart is out of your book. It's figure 4.1, and I highly recommend that you look at some of the things that are on each side. So more importantly, things like ethanol, or glucose, or sucrose, which are all sugars and gases. These are obviously going to be non-electrolytes. They don't break down. Things with multiple hydrogens sometimes, or acids sometimes, are going to be weak electrolytes. And then here, these are our strong acids, also our strong electrolytes. And so these would be things that would dissociate completely. And any ionic compounds, so ionic compounds would be like NaCl. Okay, so this is really the bulk of the lecture, and this is past the vocabulary words. This is what I want you to know. So we can classify all compounds into basically 5 types of chemical reactions. The first one is what we call a combination reaction. I'll turn this so you can see me what I'm going to be writing. So a combination reaction is something like putting 2 compounds together, and we're going to call those compounds A and compound B, and we get compound C. So putting 2 chemical reactions together has caused us to get a third chemical. Decomposition reaction is opposite. So we would take C and end up with A and B. It's decomposing or breaking down. K single replacement is a little different. This is where we have A, B, and C. and we get A, C, and B. So we see here that the C and the B have changed positions. So one of those compounds has changed positions, and because of it, we call it a single replacement. Okay, double replacement is where we have a compound that looks like this, and a compound that looks like C and D. And at the end, they both change partners. So A hooks up with B, and B hooks up with C. Okay, so this guy switch places here, and this guy switch places here. And because of it, we get a double displacement reaction. Now with the neutralization reaction, you're going to see this takes place mostly with salts. And we end up saying no reaction if nothing happens, and we'll learn how to look at a reaction and determine if something is happening or not. So let's look at our first reaction, those synthesis reactions or combination reactions. Okay. Again, when we look at something like this, we're building something. So normally it'd be A plus B yields C. Okay, building a compound. So we start with two simple substances and get a third, probably more complex substance. There's really three types of these reactions that we'll look at. Okay, so the first one is the reaction of metal with oxygen. Then we have the reaction of a non-metal with oxygen. And we have the reaction of a metal and a non-metal. Okay, so in this case, this would be A, this would be B. This would be A, this would be B. And this would be A, this would be B. And then all together, they're going to yield something that would be C. Okay, so this is the first one. This is the combination reaction, type 1, where we have a metal and oxygen. And anytime we bring a metal gas and heat it generally with oxygen, we get what we call a metal oxide. Okay, so a good example of this would be magnesium and oxygen come together to form magnesium oxide. Anytime you put a metal with oxygen gas, you should end up with some sort of metal oxide at the end. So you should always be able to determine what your end result is. Okay, same thing goes with a combination reaction where you have a non-metal and an oxygen. Most of the time they're going to form to create a non-metal oxide. So in this case we have sulfur and oxygen. Sulfur we know is non-metal, and oxygen is also your gas, and so we have to get the non-metal oxide. Okay, and then the third type of combination reaction is a metal and a non-metal that react to give an ionic compound. And so a good example of that, we know our best ions are sodium and chloride, and together they come together to produce sodium chloride, okay, which is an ionic compound. And we know it's an ionic compound because we brought two ions together. Okay, so the decomposition reaction, I think, is a lot simpler. Decomposition, obviously, anytime you see a reaction where it looks like it's breaking down, then we can kind of assume what's going on. So with the decomposition, again, it's taking C and going down to A plus B, so two simpler compounds. Generally, we need something to trigger this reaction. Normally, this would be considered kind of stable, and to get past this stage, we normally need heat or sunlight or something that will create that reaction. A good example of this reaction would be mercury oxide. And so if we take mercury oxide and we heat it, then it turns into a mercury metal and an oxygen gas. Okay, another type of decomposition metal or reaction would be type 2, and this is where we have something quite bigger. So this one here is a metal hydrogen carbonate, which decomposes to give a metal, a carbonate, a water, and a carbon dioxide. So what you really need to notice on this is that we're starting with a very large metal, or it's got metal, hydrogen, and a carbonate, and we're breaking it down. So these are all three components that it's been broken down into. And you'll see that we get, again, a metal carbonate, a water, and CO2. Okay, this you should be able to recognize as a decomposition reaction. But if you're ever given a metal carbonate, something with that CO2 or CO3, you should kind of predict that it'll break down into something like this. Same goes for a metal carbonate. So this is without hydrogen. We should always be able to predict what it breaks down into. And in this one, CaO will break down into calcium carbonate and CO2, or a metal oxide and CO2. Okay. So, moving on here, we are looking at an activity series, and this is also in your book. This is something I want you to know. And this is what we are going to use for both the decomposition reaction and the double displacement reaction. So this is something you should keep handy just to kind of understand. So the activity series is a sequence of metals, and you'll see it starts right there and ends right here. And this sequence goes in order from strongest to weakest, or their ability to undergo a reaction. Okay, so in this case, lithium is your strongest and gold would be your weakest. So here is our lithium, which is our strongest compound, and our gold, which is our weakest. Now, for our single replacement reaction, again, that's where we take A, B plus C, and we end up with CB plus A, or something to that effect, where one compound has switched out. Okay. To determine whether or not these compounds can switch, we look at that activity series. So you should have that activity series handy. And let's just look at an example. So here we have Fe and CuSO4, and again, this SO4 is kind of should be bracketed. So you can see that there's a metal here and there's a metal here. And what we want to do is see if those metals can replace each other. Okay? And we do that by going to the activity series. We look at the activity series and find those two. We see here's Fe and here's Cu. So Fe is stronger than Cu because it's before Cu. Okay, so in the case of this, Fe is stronger and it can do what it wants. So it can come and bump out Cu and take its place. And when it does, we end up with FeSO4 plus Cu. So just a single replacement occurred, and it was because this Fe was stronger. Now, how do we do this with all of them? The first thing that I want you to know is that metals that precede hydrogen in the activity series can react with anything like acids or any other compound And then those that follow the hydrogen cannot react with acids. So things like Fe, if we look at hydrochloric acid, here's an acid, right? It's aqueous, so we know it's an acid. And this compound can kind of be broken down like this: hydrochloric, hydrogen and chloride. With Fe, if we want to see if it can switch out spots, we have to look at that activity series. And so we go back again. I'm going to switch back to the activity series. And we see that Fe is clearly before hydrogen. And so we know that it can take the spot of that. Okay. And so when we switch it out, Fe pairs up with Cl. And that H2 is on its own. But gold, you know, gold is at the very end, so it comes after. In this case, we have no reaction. That Au is not strong enough to bump out that H, so we will see no reaction. Okay. There are a couple metals that are extremely violent when put with water. And so regardless of the activity series, those that are in front of the hydrogen are going to be extremely active. Okay, so I've kind of put all the activity up here. All of these are going to react with water to produce a metal hydroxide and a hydrogen gas. So here you see these metals, and instead of just looking to see if they replace that hydrogen, because this is water, we are going to produce a metal hydroxide, which would be NaOH, and then a hydrogen gas, which is always H2. Okay, same thing down here. The Ca comes before that hydrogen. It's on the list of pretty violent metals. And so we can look down here and we see that a CaOH2 is created, or a calcium hydroxide, and a hydrogen gas. Okay, the last reaction that I think we'll touch on today, we'll save no reactions for the next lecture, is going to be our double displacement reaction. So keep everything in mind for the double displacement, but we're going to add something to it. So again, double displacement is similar to a single displacement, only two things are switching. Okay. And so on this one, we use what we call the solubility rules. Learn how to read this chart. There's two of them, I think, in your book, and the biggest error that students have is that they can't read this chart. So some things that you'll see on this chart are the term solubility. Solubility means it can dissolve in water, and then insoluble. Okay. Now the thing about this chart is that there are some exceptions. Okay, so you'll read that all of these up here are soluble, all of these down here are insoluble, except. Okay, except. And so make sure you read the whole chart, because sometimes it says all of these are soluble except the one that you're looking at. Okay, so in this case, soluble in water would be things like lithium, sodium, potassium, ammonia, the acetate ion. Any of these nitrate ions are going to be considered soluble. Your halides, which would be your chloride, your barium, and your iodine, are all going to be considered soluble. Exceptions are going to be things that are mixed with silver or mercury or lead. They are going to be insoluble. Okay. Same with your sulfate ion. It's soluble by itself, but when put with these three compounds, it's insoluble. So make sure you know how to read your solubility rule chart. Okay, so again, double displacement is when we take two ionic compounds in an aqueous solution and basically switch out those front components or those metal components and rearrange them with another metal component. This is designed a little different than what I've been doing, but here you see, again, is with X, B is with Z. Double displacement would mean A would end up with Z, and it does, and B ends up with X, and it does. Okay. You can always see that the one that we're replacing is always the one in the front. So the ones in the back really aren't moving, just the ones in the front that are moving. Okay. So to determine whether or not these can occur, we look at whether AZ or the BX, so these two compounds, are insoluble compounds or whether they are soluble compounds. If they are insoluble, then a reaction occurs. Reaction occurs. If they are soluble, then no precipitate is formed. And when I say precipitate, I mean some sort of colored solution or mass that forms. If no precipitate is formed, then there is no reaction, and we just put a big NR. Okay, so let's look at these two. And unfortunately, I didn't want to pop them all up. They all came up at once. So if we look at our solubility rules for these two, okay, we know it's a double displacement reaction because this K used to be with that CrO4, which is now here. And this B used to be with Cl, which is now here. So double displacement has occurred. So let's look at our two products and determine whether or not they're soluble. Okay, and it's okay if one's soluble. We just need to see if they all are soluble. So if we look at our rules, let's go back. Remember these compounds, BaCrO4 and KCl. So BaCrO4, I see it right away. BaCrO4 is right here, the chromate ion. And it says that it is insoluble. Okay, so we know that BaCrO4 is insoluble. The other compound that we were dealing with was KCl. And if we look on here, KCl, well, we know K is soluble, Cl is soluble, and so that one is soluble. Okay, so in this case, this one is insoluble. This one's soluble. And because of it, we could say there is a reaction. This one is precipitating, and so there is going to be a double displacement reaction that occurs. Let's try this one. Okay, these are our two products. We know it's double displacement because that Na switched places with that Li, right? And so all their partners switched. If we look at NaNO3 and LiCl on this chart, on the solubility chart, hopefully you'll do this on your own, but you'll see that they're both soluble. And so ultimately, there is no reaction. So this one would not take place. So instead of having your products listed at all, you would just put a big NR. All right, I don't think that I want to get into, oh, we'll look at it. Okay, so this is an example of a precipitate reaction or a double displacement reaction. We can look at the solubility rules to determine whether or not a reaction is occurring. We can also do something that is kind of a longhand form of looking at that. And we do it by looking at the molecular equation. Okay, so here is an example of the molecular equation. Let me just pop everything up. Oh, I didn't want to do that. Okay, the molecular equation is that one right there. Now with the molecular equation, you obviously see that they switched partners. Okay, so the PB is now with the I, and the Na is now with the NO3. So they switch partners. But we need to see what is soluble and what is not soluble. So if we go and look, we find out that this one is insoluble, and this one is soluble. Okay, soluble means it breaks down. Okay, so this is a molecular equation. If we were to go into what we call an ionic equation, we would break this entire molecular equation down into ions. Okay, so the first thing that we would see is we have a PB, and so we would write down PB. Then we see we have an NO3. It's together, so let's leave it together. Okay, so we've got NO3. Then we've got an Na, an I. The PB iodine, or the lead iodide, is a precipitate, so it stays together. It's not going to dissolve in water. So we're actually going to leave it together down here. Okay, but this is soluble, so we can break it apart on the other side of the equation. Something magical will happen. So NO is crossed out with NO, Na with Na. You see that we're left with PBI and PBI2. Now we can't cross these out because they're not identical. But what we've done is we've created, we take down what's left, right? We've created just the net ionic equation, or the equation that's doing all of the work. So even though we started with this big equation up here, our molecular equation, half of it's not doing any work. The only thing doing work, or creating that precipitate, is this portion of the equation. And so we call that our net ionic equation. Okay, your homework next week will have some net ionic equations on there, or some break down the entire equation into the proper format. Okay. Now, ions that we got to cross off, this is another vocabulary word, so I'm going to square it twice. The ions like NO3, Na, NO3, Na, are what we call spectator ions. They're just kind of hanging out watching. So they're spectators. They're not doing anything within the equation itself. And so although we have water, and we have lead, and we have potassium, and we have iodine, and we have NO3, the only thing that's actually happening at the end when we process that entire equation, you see that the potassium is not doing anything, water is not doing anything, NO3 is not doing anything. The only thing you see doing anything are these ones clumping together down here, which are the iodines and the PB. And so those are the only ones that have done anything within that reaction. And that ultimately is how we get a precipitate, or the change in formation. Now, if you'll notice, this liquid is clear, and the substance that's being dropped in is clear. So what's forming is a completely new compound. All right. This is another solubility rule thing. It says the same thing. This is also located in your book. And so make sure you know how to read it, because this one also lists soluble, except, insoluble, except. Okay, so make sure you understand some of those solubility rules. These are different forms of precipitates. So obviously here, this one formed an orange precipitate. This one kind of formed an ashy or chunky. This one has a green precipitate, and that has a cloudy white precipitate. All of those can be considered insoluble compounds or precipitates. Okay, and if you go to your solubility chart, you'll notice that all of those are insoluble. If they're soluble, all you would see is just the clear liquid. You wouldn't see all the other gunk in there. Okay, so let's try and classify these on your own. Classify these compounds as either soluble or insoluble. You have about 3 minutes to look back on your chart and do that. Okay, hopefully all of these were easy enough that you just were easily able to look at that chart and find out that AgSO4 is insoluble. Okay. This one is a calcium, which is in the group metal 2. Therefore, this one is insoluble because it's mixed with that carbonate. And we have this one here, which you won't find on the rule chart, and so we know it's soluble. Okay, the PO4s and NAs are soluble. Good. I think we're going to stop there. We'll pick up with the net ionic equations in the next lecture on how to write them and how to prepare them. Do lots of practice problems. I don't want this to be the main focus of your quiz this week, so I'm going to leave this off. And then we'll cover it the next